Okay, we started talking about kinetics, so we're going to talk about some of the rest of this and do a few more examples of stuff we did last time. But last time we got into kinetics, which is obviously really kind of a study of how fast or slow a reaction sort of proceeds. And we talked about a couple of things, specifically, we talked about what's sometimes referred to as the rate expression. And the rate expression really allows you to sort of relate everybody in the reaction in terms of how they're changing with time. So for example, here we could say that the rate is equal to minus 1/2 the change in the concentration of A over the change in time. Remember that when we do write the rate expression to take into account the stoichiometry that's in the equation, we take 1 over the coefficient, and that's sort of, again, as we talked about last time, does the stoichiometry part of the calculation along with the kinetics part of the calculation together. It is negative, as we also talked about, because it's a reactant. So over time, we should expect that the concentration should be decreasing with time. And that will equal negative the change in concentration of B over the change in time. Here, the coefficient is 1, which basically gives you 1/1, which is why people obviously don't put it in because it is just 1. We still have the negative here because it is still a reactant. When we get to the product side, we should expect it to start increasing with time. So we do have it as positive, and that'll be 1 over the coefficient there, change in concentration of C over the change in time. The idea here is this is usually your average rate. That's usually a positive number. And because our reactants are decreasing with time, when you do final minus initial concentrations here, you will end up with a negative number. And that negative number and this negative that is in front will turn the average rate into a positive number, which is what it should be. You could kind of relate them all together. You could really just pull out, like we did in a couple of those examples, just the parts that you're interested in. And the relationship, again, if you're going to do something like that, is the rates equal minus 1/2 change concentration of A over change in time. The rate is equal to, say, 1/3 change concentration of C over change in time. The idea here is just to say you know how A is changing with time. That would allow you to figure out the average rate for that reaction. The benefit of that is the same number that would be over here. And then that would allow you, for example, to figure out how C is changing with time. So that is how you could kind of relate these guys to each other. We also talked about that you could, if you wanted to, kind of do more of a stoichiometry problem first and then kind of do the kinetics part of it as well. It works the same way. The other sort of major thing that we talked about last time was the rate law, and the rate law has a general sort of form that looks something like this. And here, X, we have our rate for the reaction. That is our rate constant. And again, the rate constant is a constant value for a particular reaction at a specific temperature. X in this example and Y in this example are what are referred to as the orders with respect to A and B. You can again think about, as I talked about last time, sort of the orders are the proportion that you sort of need of each of those reactants to maintain a specific rate. One of the benefits of sort of knowing the rate law in a particular reaction is you can actually use that to your benefit if you, for example, find that you're working with a reaction that's maybe going too fast. You could play with the concentrations and you could slow it down if you needed to. You could also, if you have a reaction that's maybe going too slow, you could also play with concentrations and perhaps speed up the reaction. So the benefits of sort of knowing the rate law is very useful in a real life situation. Now, when we talk about the rate law, it is something that is found experimentally. So this is always sort of found experimentally. And the orders are not the coefficients from the balanced equation. And that usually means that usually in these problems, you have a table where you have a number of experiments listed. You usually will have the concentration of your reactants listed, and you will usually have an initial rate listed for each of those sort of experiments. And probably the best way to sort of figure out the orders is, as we talked about, you could do this sort of mathematical approach where you take rate 2 over rate 1. And the idea when you're sort of choosing this is you want to come to the table and you want to find two entries in that table, two different experiments, where one of the concentrations stays the same. So, for example, if A stays the same and B varies. And what that will give you is basically one unknown. You would put into here, for example, if I chose 1 and 3 in my example, and 3, by the way, if it had like the larger rate, I would put that probably up on top. Again, it'll give you the nicer whole numbers. You can do it the other way, just get more of a decimal sort of form. But if you do this, you put everything from, say, experiment 3 up on top, everything from experiment 1 on the bottom, and it will kind of cancel out. Again, you'll get something maybe like 4. And then at this point, we don't know what that is, but it is a constant, so it should remain the same. And since the x's here should also be the same, and the concentration of A is constant, those guys would cancel out and maybe get like a 2 to the y, where y would equal 2. Again, you can take the natural log of both sides if you don't have a nice pretty number that's happening, and then divide it to the other side, and you'll end up with the same answer. So that is, again, mathematically how you solve it. The idea is you would use the table of information to figure out the orders. Once you have the orders, you then could have the completed rate law, and then you could go back in and solve for something like what the value of the rate constant is by putting in the values from the table. And when you go to the point where you're solving for the rate constant, it doesn't matter really which entry you choose. They all should give you basically the same rate constant because it should be a constant value. Any questions on any of that there? All right, so we did a couple examples. Why don't we do a couple more here just to make sure? So let's try this one here. What is the rate law? What are the orders, the overall order, and what is the value of K? Okay, so let's take a look. So once again, in this case, we could write sort of the generic rate law here before we figure out the orders. The rate is equal to K times concentration, in this case, of NO2. We'll make that an X, and CO, we'll make it a Y. Remember as well, kind of a difference between the rate law and the rate expression. The rate law only deals with reactants, so no products in the rate law. So remember, when we're doing this, we're looking for two entries where one of the concentrations stay constant and one varies. So just looking at it here, 1 and 2 will achieve that for us. That's going to keep the CO constant and vary the NO2. So if we look at experiments 1 and 2, again, we're going to take the larger rate on top. You don't, again, have to do that, but it gets you a little bit nicer number sometimes. So I'm going to put number 2 up on top. And what I'm going to do is basically just put all the information for experiment 2 up on top. And in this case, my concentration would be 0.2 to the X. And my other concentration there would be 0.1 to the Y. We're then going to put everything for experiment 1 there on the bottom. And again, here we got 0.1 to the X and 0.1 to the Y. Once again, we're just going to divide everything out here. So 0.0082 divided by 0.00821. Going to give us basically a 3.9, which is pretty close to 4 in this case. That will get rid of the K's because they are constants. When we divide that, that will give us a 2 to the X. And once again, although we don't know what Y is, it is the same on top and bottom, which means that should completely cancel out. Again, in this case, I'm going to round it. It's close to 4. And that means that in this case, X would equal 2. Any questions on that there? Again, you could take the natural log of both sides and divide it. So if you were to do that, you could take the natural log of 3.9. It equals, divided by the natural log of 2, it equals, and you'll get basically like a 1.96, which again is fairly close to 2 if you kind of do that. And sometimes they may not be perfect numbers. You can do a little bit of rounding because they are based on experimental information. So same thing with the experiment you did yesterday. Again, you could probably round to the closest whole number when you do solve for the orders. Now that we kept CO constant, we then want to go back and keep the NO2 constant. It looks like in this case, we can't go with 2 and 3. And by the way, we could also have done on the first one, 1 and 4 or 2 and 4 as well. It should come out basically the same. So we're going to look at experiments 2 and 3. And here we're going to go with, I guess 3 is slightly larger, 0.0083 molar seconds up on top are 0.2 to the X, 0.2 to the Y. Putting number 2 on the bottom there, 0.0082, K, 0.2, and 0.1 here to the Y. When we do this, basically get 1. Again, our K's will cancel. These guys are completely cancel. And when we do that, it's going to give us a 2 to the Y. A reminder, right, that if you take something to the 0 power, right, that is what's going to equal it. 1. And again, if you take the natural log of 1, you will get 0. And divided by natural log of 2 will give you 0 as well. So that is the orders for this reaction. That means that our really completed rate law is the rate is equal to K times NO2 squared. Now, because the CO is 0 order, you could do one of two things. You could leave it off in terms of the rate law like I did here and not even have it in there. If you are to put it in, you do need to make sure that I'll just go underneath here. You write it like this, and you do put a 0 on top of it. Because if you do not put the 0 on top of it and just put it in with nothing right in there, it is implied that it is first order, right? So you got to make sure if you do want to include it, you got to put the 0 in this particular case. Again, if you don't put that 0 and you leave it in there, people think it's first order. So probably could just leave it out since obviously it's not going to be the one that's affecting the rate at all. The overall order in this case would then be 2 plus 0, which is second order overall by just adding those guys together. Now that we do have the completed rate law, we could solve for the rate constant. K would equal the rate divided by NO2. And again, we do need to square it. At this point, we could absolutely choose any one of these entries in this table to solve for it. So I'm just going to take the first entry, and that would give me 0.0021 molar seconds divided by our NO2, which is 0.1 molar squared. And that will get us here. What's in there? Looks like 0.21. In terms of the units, molarity on top and really one of the molarities on the bottom will cancel, gives us 1 over molar seconds as our units. By the way, again, as we talked about yesterday, that is 2 letters, which matches the second order type of thing. Any questions on how to do that there? All right, so that's just one more example like we did yesterday, and obviously it's very similar calculation to what you need to do for the lab that we did yesterday as well, and obviously you're responsible for that for the final. All right, let's take a look then at some other stuff here. Now, we talked about sort of reactions and overall orders of reactions, and there are a few very common types of orders for reactions that we come across. There are first order, second order, and zero order reactions. Those are probably the most common ones. They are based off of really how many reactants you have, for example. So if you think about just in general, when you've seen a chemical reaction written or a chemical equation, I would say probably most of the time when you look at a chemical reaction, you probably have maybe 1 reactant, 2 reactants, occasionally 3 reactants. You don't usually have like a, 4, 5, 6, 7 things reacting at once in a particular chemical reaction. So this is why typically when we think about overall orders of reactions, we only have a lot of times very commonly first, second, zero order reactions, because in order to get something like, say, a seventh order reaction, you would need a lot of things probably reacting at once to get something happening in that case, and that usually doesn't happen. So a very common type of orders of reactions, which are important for a couple of reasons, and if you're taking 200B, you will see them again. This is a reaction where if we have one reactant, it would have a order of 1. You could also get a first order reaction with 2 reactants where one is first order and one zero order. Will also give you an overall first order reaction. You can write a rate law for first order reaction. Rate is equal to K times concentration of A. And if we solve for the rate constant, we end up with units which are really important, which are reciprocal seconds. So the typical units for a first order reaction for the rate constant are reciprocal seconds. They don't necessarily always have to be reciprocal seconds or 1/seconds, but they are basically 1 over some unit of time. They could be minutes, hours, weeks, days, years, whatever it may be. But most commonly when we do experiments, kind of like the experiment you did yesterday, most of the time is like in seconds. It's a very common sort of unit of time that we use. So a lot of times 1/second. The importance of the rate constant, as I mentioned before, is there are some specific equations that are used for first order, second order, and zero order type reactions. And you do need to make sure that you apply the correct sort of equation when it is first order versus second order. And again, it is the rate constant units that oftentimes will allow you to know what type of reaction that you're dealing with. And they will not a lot of times just come out and kind of tell you what order it is. They'll give you that rate constant with the units. There are 2 very common sort of graphs, and as I mentioned before, kinetics is all about graphs. They like graphs for everything that we see with first order. If you graph the concentration of A versus time, you would see what we expect, this sort of decreasing graph here with time of the concentration of A. As we would expect, A needs to go to products, which means we should expect it to be decreasing with time. But in kinetics, it's all about the straight line and the y equals mx plus b type of situation, and that's the equation for a straight line. So this is what is referred to as the integrated rate law for first order. It is the natural log of A is equal to the natural log of A naught minus KT. This is like your final concentration. This is like your initial concentration. K is your rate constant. And T is actually time here. Again, not temperature, so that's actually time. So if you take this integrated rate law, and you rearrange it, you take the natural log of A is equal to minus KT plus log of A, there you go, the natural log of A naught. This would be written in the form of basically a straight line. And this would be our y is equal to mx plus b. So this is where we get really our linear relationship for a first order reaction. If we graph the natural log of A on the y, and if we graph the time on the x, we could get a straight line. And this line will have a negative slope, where if we take the slope of that line, we could graphically determine the rate constant for that reaction, which is a common sort of procedure. The slope will equal minus K. So once again, the slope will equal minus the rate constant. That is because if you take the slope of this line, the slope will actually be a negative number. Negative number for the slope will turn your K value into a positive number actually when you pull it off. So graphically speaking, you can do a kinetics experiment. You could graph the natural log of A versus time for a first order reaction. You should get a pretty linear relationship that occurs. There's also with these type of orders what is referred to as the half-life equations. And the half-life equation is the time that it takes for half of whatever you have to basically disappear. So after the first half-life, if you had 10 of something, you would have 5, and obviously you would have 2.5 after the second, and so forth. For a first order reaction, the half-life is equal to the natural log of 2 divided by the rate constant. And very commonly, a couple of things with these equations that you do want to be careful of is really this part of it. The rate constant unit for time and the unit of time does need to be in the same unit. So very commonly, for example, maybe your rate constant is in seconds, maybe your time's in minutes. So you got to make sure those guys sort of agree and convert. So when you think about a first order, really or any type of order reaction like this, there's really kind of 4 important things to know: the value of the rate constant in terms of the units, which tells you it is a first order, the typical graph that you see for a first order, the integrated rate law, which allows you to figure out how concentration is changing with time, and also the half-life equation. Now, very commonly, in addition, the half-life equation and the integrated rate law are used together, and a lot of times you're given enough information uh, except for the rate constant. So it's very common sort of practice to use the half-life equation to figure out K, and then go into this equation to figure out whatever you're looking for. So very commonly they do go together. As I mentioned before, first order kinetics is an important one. All radioactive decay follows first order kinetics. So anything that's radioactive will follow this type of kinetics. And it's important, again, to take 200B, you do a whole nuclear chemistry chapter. So you'll see these equations all again, and you'll have to sort of use them in that application. So for example, just to show you how to use this equation, since you might see it again, the reaction of 2A goes to B is first order. It has a rate constant of 2.8 times 10 to the minus 2 reciprocal seconds at 80 degrees Celsius. We want to know how long will it take for A to decrease from 0.88 to 0.14 molar. So a couple important information that we pull out. We do have the rate constant, which is 2.8 times 10 to the minus 2 reciprocal seconds. We do have the initial concentration of A, which is 0.88 molar. We do have our final concentration of A, which is 0.14 molar. They were nice enough to tell us that it is first order, but a lot of problems, they are not nice enough to tell you that. The reason you would know it is first order is because you see these units here, and that will tell you that it is a first order reaction. So again, if they don't tell you that, that is what those units will tell you. That should also direct you to our first order integrated rate law, which would look something like this. And obviously in this case, we do have our final, our initial, and we do have the rate constant given to us. So to solve for it, we would just plug in what we need. Now, to solve this personally, I would take on my calculator the natural log of 0.14 and hit equals. And then basically I'm going to take this thing here and subtract it to the other side. And I would then subtract it from the, bless you, natural log of 0.88. At that point, that will give me minus 1.838279 equals negative 2.8 times 10 to the minus 2 reciprocal seconds times t. Obviously, we're going to just divide that now to the other side. And we're going to take it to the other side and not forget to also take the negative sign. And that's going to give us a time that's equal to 66 seconds. So it will take about 66 seconds for this reaction to drop concentration from 0.88 to 0.14. Any questions on that there? So as I mentioned before, the half-life equations are also really important in terms of kinetics. And again, especially in terms of first order kinetics, it is equal to the natural log of 2 over K. You will also sometimes just see it as 0.693 over K. That is what you get if you take your calculator and take the natural log of 2, you get 0.693. So in this case, the half-life decomposes at a rate constant of 5.7 times 10 to the minus 4 reciprocal seconds. In this case, we want the half-life. And again, we take the natural log of 2 divided by our 5.7 times 10 to the minus 4 reciprocal seconds. And that will get us here. About 1216 seconds in this case would be the half-life, which is approximately 20 minutes. Every 20 minutes, there's a half-life that's happening. By the way, I know that this is the proper half-life equation to use. Once again, because I see the units here, tells me it is first order. So that is how I know. I want to make sure that I use the first order half-life equation, not say the second order or zero order one. So as you can see, after every half-life, we do lose half of whatever we started with. After about 10 half-lives, pretty much gone at that point. And again, first order, definitely the one that is used for radioactivity. All right. So we'll skip that, I think. Let's talk a little bit about some of the other orders, very common orders of reactions that we take place. And that is second order. And second order reactions can really be achieved also in a couple of different ways. You could have obviously one reactant that is second order. You could also have two reactants that is first order each, which will give you an overall second order. Now, if we do kind of the same thing and write the rate law here for our second order reaction, we will get the rearranging and solving for K will give us our molarity on top will cancel, will give us 1 over molar seconds as the typical units that we see in a second order equation. Now, when we look at this, that is different than, again, 1 over seconds, which is typically what we see for first order reactions. It also has a integrated rate law that involves temperature, not temperature, time and concentration. And that is 1 over A is equal to 1 over A naught plus KT. Again, this is the same stuff. That is our final concentration. That is our initial concentration. That is our rate constant. And that is our time in this case. It has a different half-life equation, and the half-life for a second order is equal to 1 over K times the initial concentration. So unlike first order, which is independent of the initial concentration of your reactants, the half-life of a second order reaction is actually dependent on the concentration of your initial reactant. Obviously, in this case, as you can see, it's on the bottom. So perhaps if you have a larger concentration, you'll end up with a shorter half-life, right? Because that'll make a bigger number on the bottom. And when you divide it, perhaps you'll get that type of situation that occurs. So in this particular case, we also can rearrange this in the form of a straight line, which is very common in terms of our kinetics here. And that's going to be y is equal to mx plus b. And the typical graph that we see for a second order is on the y, we graph 1 over the concentration of A. On the X is still our time. Different than first order is we will actually get a positive sloping straight line. And the result of that is we will take the slope of it and it will equal the rate constant. So that is, again, graphically how you can do that as well. So I might have misspoke. As you get larger, you actually get a smaller one, since it is 1 over the top there. We can't graphically find that. So much like our first order, the kind of 4 important things here, we have our rate constant units, we have our integrated rate law, our half-life, and again, the very common sort of graph that goes with it. The last sort of type of reaction that we come across a lot are zero order reactions. And zero order reactions, again, can be achieved by one reactant where the order is zero. And obviously, as we know and talked about, if the order is zero, that means that it does equal one. In this case, that means that the units for a zero order sort of reaction overall actually will be the same units as the rate, which is molarity over seconds. It has a rate law that looks very much like first order without the natural log. So it is the final concentration is equal to the initial concentration minus KT. And if we do our half-life here, also dependent on the initial concentration divided by 2K. In this case here, if we have a larger concentration, we will have a longer sort of half-life that's happening in this case. If we rearrange our rate law here for second order, again, we in form of a straight line, we will give us y is equal to mx plus b, and the graph that we typically see is the concentration versus time. This is actually the same graph that we saw for first order reactions. The difference is what the graph looks like. If you graph concentration versus time and you get this linear relationship, you are looking at a zero order reaction where you can't take the slope of it and will equal again negative k. And again, this is a negatively sloping line, which means that our slope will be negative, and that negative will turn RK into a positive number when you solve for it. Now, if you were to look at the graph that we saw earlier for first order, which was concentration versus time, it is not a linear relationship. It is decreasing with time. So although they are the same things graphed, the only one that should give a linear relationship would be if the reaction is zero order when you do the concentration versus time. The same four things are important to understand that it is a zero order reaction, definitely those units, and it has specific type of equations that go with it. So for example, if we were looking at this and we were told it is a second order reaction, and we have the initial concentration of Q in this guy, which is 0 0.00, too many zeros, 1, 0. And our final concentration of Q is 0 0.0010. And we do have the time here, which is 5 times 10 to the 2 seconds. In this case, we're actually looking to find the rate constant. And because they did tell us a second order, we would use our specific second order equation, which looks like this. And obviously just plugging it in this case here, 0 0.001 equals 1 over 0 0.010 plus k, which is what we're looking for, and our time, which is 5 times 10 to the 2 seconds. Again, here, mathematically, I would take 1 divided by 0.001, and then I would subtract this guy to the other side, and that would then mean minus 1 divided by 0.01. Going to give us basically 900 is equal to k times 5 times 10 to the 2 seconds. And that is, by the way, 1 over molarity is the units here, as these are molarity. Dividing our 500 basically to the other side, divided by 5 to the 2, will give us a rate constant of 1.8. And again, when we divide that seconds to the other side, will give us 1 over molar seconds, which is our units that we see for a second order, again, dividing this to the other side. Any questions on that one there? So again, those are 3 very common orders of reactions: first order, zero order, and second order. They have specific sort of integrated rate laws, which relate basically concentration and time as they change. Again, you definitely will see first order kinetics once again in 200B. As I mentioned before, pretty much all radioactive decay follows that sort of kinetics. So again, if you're off to 200B, that is those guys you will see again in that chapter for sure. All right, so as I mentioned before, graphically we can determine based on the graph what order of reaction that we have. If you have concentration of A versus time, natural log of A versus time, or 1 over A versus time, whichever one gives you the most linear sort of graph will tell you the order. So graphically, you can make all three graphs and basically just do a best fit line, and the most linear relationship will give you the order of that reaction. We're going to talk about the relationship of sort of kinetics and temperature as well. So these are some energy diagrams, and the one on the left is a exothermic, the one on the right is an endothermic. This is your reactants, that's your products. This is your reactants, and that's your products, basically. And in terms of energy, reactants has to go up the hill and to the other side. And this is an exothermic reaction because our reactants are higher in energy than our products, which means energy has to be given off in order for basically our reactants to get down to our products. So whenever you have an energy diagram where reactants are always higher in energy starting with than your products, it's going to be exothermic because of that. We talked about delta H a little bit, which is the change in enthalpy, and that is how you do that. You basically take the difference between those two, if I could draw a straight line, and that would give you the delta H of your reaction there. And the reason that happens is because the delta H of the reaction is the delta H of your products minus the delta H of your reactants. So clearly our products are a lower number, smaller number, right? Minus a larger number is going to give you a negative value. And that's why delta H's that are negative are exothermic because of that. That is different than what we see over here. Our reactants are actually lower in energy than our products. In order to get there, you got to kind of put energy in and be absorbed, which is making it endothermic type reaction. Same idea if you take the difference between where the products end and where the reactants start, that would be your delta H of your reaction. That's a really bad straight line. We'll do it that way. And the same idea in this particular case. If you just look at the graph, if you take the delta H of your products minus the delta H of your reactants, on the graph, our products are a larger number than our reactants in terms of energy. Minus a smaller number gives you a positive number for delta H. So this is why when we see a delta H value that is positive, it indicates a endothermic reaction that's occurring because of that difference. Now, when a reaction takes place, remember that there's kind of two things that has to happen for a reaction to take place. You have to have a collision, which means the molecules do need to collide with each other. They do need to actually collide with each other, and two things actually do need to happen. They actually need to hit each other in the right location. So they do have to kind of collide in the correct sort of active spot on both reactants. In addition, they do need to have a sufficient amount of energy when they do collide with each other. That amount of energy is what is known as the activation energy, or E of A. The activation energy is basically the minimum amount of energy that's required for a reaction to take place. As you can see on this graph, it is essentially the hill that the reactants have to climb. So it's this big hill that the reactants have to climb to get to the other side. Same thing here. If you look over here, it is this big hill that the reactants has to climb basically to get to the other side. So the reason the activation energy is important is you do need to have that minimum amount of energy for that reaction to take place, which means there may not be a great amount of reactants that have sufficient amount of energy to actually get up and over that hill. So that affects the rate of the reaction. So for example, if I have a relatively small hill to climb, there's probably going to be more reactants that have enough energy to get up and over that hill to the other side, and that would result in the reaction happening probably a lot faster or have a faster rate. If I have a bigger hill to climb, that means there's probably a less of a chance that there's a great number of molecules that have that amount of energy to get up and over to the other side, and that usually will result in sort of a lower rate or speed of that particular reaction. Like if you had to walk over a speed bump in the parking lot, it's like this big. Most people will have enough energy to go and do that. You had to go climb the mountain on the side of the road there, right, all the way to the top. There's not going to be a lot of people that can go climb up to the top of the mountain. So it's going to take you a lot longer to do that. It take a little bit more energy to get up and over to the other side. Now, as this is happening and as we go from reactants to products, remember that we are breaking bonds, and that's pretty much what's happening. So as we come up this hill, we basically have something that is breaking their bonds and actually starting to form new bonds. And when you get to the very top of the hill, this is what is referred to as the transition state, and it is sort of the highest point in energy. And as hopefully you know, in terms of energy in chemistry, high energy is not really the most stable situation. Pretty much most things that happen is in an effort to lower the overall energy that's happening. And when we hit this highest point, which is a transition state, we have a complex, which is sometimes referred to as the activated complex, our transition state complex. And that is a guy that has partially broken bonds because he's trying to break his bonds, but also partially made bonds. So it's a very unstable sort of intermediate. And usually very quickly it will kind of drop down the other side of the hill to the products as a result of that. So activated complexes on transition state usually arise from these sort of partially made and broken bonds, and it doesn't hang around a lot. So the size of the hill does play a direct effect, obviously, in how fast or slow the reaction takes place. And even just from this two pictures here, you could clearly see in an endothermic reaction, we have a much greater hill to climb, which is why overall we need to throw some energy in there to get everybody kind of up and over the hill to the other side. Now, there is an effect of temperature on that. And by the way, before we move off, one way that you could also speed up the reaction is by using a catalyst. And what a catalyst does, again, is it is something that sort of facilitates the reaction happening a lot more efficiently, is the way you could look at it. And ultimately, what it does by finding sort of a alternative pathway for that reaction to take place, it is actually able to, when you look at sort of a reaction like this, it is able to essentially lower the activation energy. So when you add a catalyst, what it's able to do is lower that activation energy. And the result of that is because the activation energy is lowered, there's going to be a greater proportion of molecules that have enough energy to get to their side. And that should normally increase the rate of the reaction because there's going to be a lot more reactants basically being able to get to the product side. So a catalyst, as I mentioned before, can be, for example, like a solid. And if you have gas molecules, instead of, say, gas molecules just flying around trying to find each other to react, maybe they are slightly more attracted to the solid. So they head towards the solid. And what that does is it puts everybody closer in contact with each other, going to sort of increase the rate at which they will react with one another. And you will see that increase in reaction rate. So there is, again, what is referred to as the Arrhenius equation. And that is the equation that basically will relate temperature to our rate constant. And there's two versions of the Arrhenius equation that you sometimes come across. This is the graphical version of the Arrhenius equation. And what we see here is, in terms of temperature and the rate constant, is what we talked about. At a lower temperature, we have a much slower reaction or a lower rate constant. When we increase the temperature, we see a much higher rate constant, and the reaction is going to proceed a lot faster. So again, as we talked about, I think yesterday, if you raise the temperature about 10 degrees Celsius for a lot of reactions, that's enough to make the reaction occur twice as fast as it normally would. This version of the Arrhenius equation here, which is K is our rate constant, E of A is our activation energy, R is the rate constant, but it's actually, again, the one that involves energy. Temperature is the T here. It doesn't need to be in Kelvin, and that is our frequency factor in this case. The frequency factor you can kind of think of as the proportion of molecules that have a sufficient amount of energy basically to get to the other side. And the activation energy, which is our hill that they have to climb. When you look at this equation, if you're ever to sort of mathematically use this equation, there is, again, an important part of it that you want to make sure, which is this part. Unit-wise, typically speaking, activation energy is usually given in kilojoules, and R is given in joules. So again, you have a 1,000-fold difference. So mathematically speaking, if you ever kind of use that equation, you got to watch the units there. Otherwise, you will be off on it by a factor of 1,000 in this particular case. Now, if we rearrange this equation and write it like this is going to give us our linear relationship that we have, mx plus b. And once again, this is the typical Arrhenius plot that you sometimes will see. And on the y-axis, we'll have the natural log of k. On the x-axis, we will have 1 over the temperature in Kelvin. And that should yield you a straight line with a negative sloping line. The purpose of this and why you would do this is if you want to sort of graphically figure out what the activation energy of that reaction is. The slope in this case, which is right there, is equal to minus E of A over R. That means that if you graph this and you figure out the slope of the line, by the way, that is negative value in this case, you can times it by R and you will get the activation energy. By the way, the activation energy is usually a positive number. As you can see in the graph that we saw before, they are all positive hills going upwards. So activation energy is usually a positive value. So this is a very common sort of experiment, also known as part 2, I think, of our experiment that we didn't do, is this. And you can very easily sort of graphically determine the activation energy by taking some values, much like what you did, some rates, and do it at some different temperatures. Why we had for example, an ice bath and a hot water bath, to do it at some different temperatures, and you can do this plot. Now, when we look at this graph here, it does give us that straight line. And again, if you were ever to do this, you would have to do some conversions of some information given to you. For example, if this was a problem, we would need to take 1 over K, or the temperature here, and then we would have to take the natural log of K of all these values, and you would have to then graph it. And if you do kinetics problems, typically Excel is your friend because you have to make a lot of graphs a lot of times. And you would get a graph like this in this particular problem. And again, we can use the information. This again is our y is equal to mx plus b. And again, this number up here is our slope. So if we wanted to know the activation energy, E of A over R is equal to the slope, we could actually just pop those numbers in. Minus E of A over R, 8.314 joules per Kelvin per mole, is equal to our negative 1.12 times 10 to the 4 in this case. Again, those two negatives going to turn our activation energy into a positive number. Essentially, we're just going to multiply our slope by R. And if we do that there, we will end up with an activation energy of 93116.8. The units here are going to be joules based off of this. And if we divide it by 1,000, which is typically what we would do, we would give our answer in kilojoules. So just graphically from this, we could also figure out our activation energy in this case, which is 93.1 kilojoules. We could use the y-intercept here as well to figure out the frequency factor. And again, the natural log of A is equal to the y-intercept. So we could also plug the numbers in as well. So that's a very common sort of graphical approach when you're doing kinetics, to use the Arrhenius equation to figure out things like activation energy or frequency factor. More commonly, though, nobody wants to do graphs. So more commonly, though, in terms of the Arrhenius equation, as long as you have kind of 2 points along that line that you would graph, so that straight line that we just saw in that graph, if you know 2 points along that line, you could actually just mathematically solve for it. And that's the natural log of K2 over K1 equals E of A over R, 1 over T1 minus 1 over T2. These are basically our rate constants at 2 different temperatures. This is our activation energy. That is our rate gas constant, which is again the one with energy. and these are our temperatures that do need to be in Kelvin. So this is more commonly probably than the graphing aspect of it. You could just plug and chug into this equation. If you know the two rate constants and one of the temperatures, you can figure out the other temperature. You know, two temperatures and one rate constant, you can figure out what the other rate constant would be. As you would typically see is obviously as the temperature goes up, we would see an increase in the value of the rate constant. And as the temperature goes down, we would see the rate constant decrease with time. All right, so the last thing we're going to talk about in terms of kinetics is the idea of mechanisms. And mechanisms, as we talked a little bit about yesterday when we were doing the experiment, is a way to sort of describe how a reaction takes place. Now, not all reactions, as I mentioned before, is sort of a one-step sort of process where it goes from reactants directly into products. So many reactions happen in kind of smaller individual sort of steps. So, for example, perhaps the first thing that happens is A plus B makes C and D, then C and D react to make E and F. And maybe this is a two-step mechanism where if you add them together, much like we did with redox reactions, anything that's on opposite sides of the arrow will cancel. And in this case, C and D would cancel. And that would leave us our overall reaction. Everybody stays on the left-hand side and everybody stays on the right-hand side of the arrow and gives us our overall reaction. So when we have sort of a mechanism for how a reaction may take place, these are what are referred to as elementary steps. And elementary steps are individual steps that, when put together, will give you your overall reaction that you're looking for. So for example, here, if we look at this overall reaction, 2 of NO plus O2 goes to 2NO2. Although we do not see it anywhere written in the overall equation, when this reaction takes place, N2O2 is detected. So even though we do not see it in the overall reaction, it does pop in there at some point during the process of this reaction taking place. So that would imply that this reaction does not occur just in like a one-step fashion going directly from reactants to products, as again, N2O2 is not present there. So this would imply that perhaps there are multiple steps for this to occur. So one proposed mechanism is a couple of the NOs make N2O2, which would account for why we do see it in the reaction happening. Then that N2O2 will react with some oxygen to make some NO2. The N2O2 actually will get canceled out by the time the reaction is done, and that gives us our overall reaction that we're looking at. This is a plausible mechanism for how this reaction will take place. The N2O2 in this case would be considered what is known as an intermediate. And an intermediate is something that is made in a reaction mechanism early on, but gets completely used up by the time the reaction is over. So it's no longer present when the reaction is over. It gets, again, completely used up. So mechanisms basically are there as plausible explanations of how a reaction may take place. Doesn't mean that it's exactly correct in all cases. It may not be. Doesn't mean it always happens in that way. It may not, but it is sort of a way that we could sort of explain how a reaction may take place. Now, when we look at a reaction, as I mentioned before, we do have an intermediate. And the intermediate, again, has to be something that was made early on in the reaction, but did get completely used up by the time it was over. An intermediate cannot be found in the overall reaction when it's all said and done. It can only be found sort of in the steps. When we look at these individual sort of steps, these elementary steps, they can be classified by the molecularity of it. A unimolecular reaction means that there's only one thing reacting. Bimolecular means there's two, and termolecular means there's three. Each of these would be considered a bimolecular elementary step, as they both have two things reacting in these individual steps. Now, what is a mechanism important, and how do I know if a mechanism is really a good mechanism or a bad mechanism for a particular reaction, where there's a couple of things that you want to look at in order to determine whether or not a mechanism is a plausible mechanism for this reaction to take place. Now, the first thing is there is really only one place in kinetics where you can use the coefficients as the orders when you write a rate law. And the only place that you can do that is when you're doing mechanisms and these elementary steps. So within elementary steps, we can actually write rate laws for each of the elementary steps. And when we write a rate law for each of the elementary steps, we actually can take the coefficient as the order. And again, that is the only place where you can do this before you have to do, obviously, the calculations like we did previously. So here, if we were to write a rate law for this elementary step, the rate would equal K times A. Here, the rate would equal K times A times B. And here, that's basically 2A, which means the rate law would be K times A to this 2. So why this is important, you can write the rate law using the coefficients for the individual elementary steps is in order to determine whether or not a mechanism is sort of a good mechanism or bad is there's two things that you need. The first thing is you need to take all the steps, and when you add them together, you get rid of all the intermediates and you put them together. All those steps add up to the overall reaction you're looking for. So for example, like I just did there, A plus B goes to C plus D, C plus D goes to E plus F. The overall reaction I was looking for was A plus B goes to E plus F. So when I add these steps together, check, I do get that overall reaction. Clearly, if you added up all the steps together and you don't get the reaction you're looking for, that's probably a pretty bad mechanism. It's not going to be a correct mechanism. But one thing that you have to make sure is that all those steps, when you put them together, get rid of any intermediates that are present, it does add up to that overall reaction. The second and most important one is Pro L is that the rate determining step should have a rate law that matches the one that's found experimentally. And we touched upon it yesterday when we were talking about the experiment we were doing. The rate determining step, which is sometimes referred to as the RDS, or rate determining step, is really the slowest step in the mechanism. And it is always the slowest step in the mechanism, which ultimately determines how fast that reaction can take place. So, if there's multiple sort of steps that has to happen, and somewhere along the way, there's like a really slow part of that mechanism, that's going to ultimately determine how fast this reaction takes place. So the rate determining step should always have a rate law that matches the one experimentally. So if you look at the experiment, for example, that we did yesterday, if you look at the overall reaction, but then you look at what you're trying to find the rate law for, the rate law that you're trying to find is actually for the slow step in the mechanism, because that is the one that should be the same as the one you find experimentally. It is not finding the rate law, for example, for the overall reaction that you have, because we're looking for the one that's based on the slow step. Because in the overall reaction that we did yesterday, there is no iodine present, right? But that is what you're trying to find basically your rate law for, because that was based on the slow step and is really the one that determines the mechanism of the reaction and how fast or slow it will take place. So how do we do that? So for example, if we have something like this, the experimental rate law for this reaction between NO2 and CO to produce NO and CO2 is the rate is equal to K times the NO2 squared. So this is our experimentally found rate law. And this is a possible mechanism of how this reaction takes place. So if we want to kind of know, is this the overall good mechanism or is this a plausible mechanism? We want the overall reaction. Basically, what we're going to do is add these two steps together. And basically anything that's on opposite sides of the arrow can cancel out completely or reduce down. So those guys would all cancel. And that would leave us an overall reaction of NO2 plus CO goes to NO plus CO2. And again, after whatever we cancel out, everybody on the left stays on the left, everybody on the right stays on the right. Now, what is the intermediate in this case? The intermediate in this case is actually only NO3. Now, sometimes people are like, didn't we also cancel out this guy? And the answer is we did, but we didn't completely cancel out that guy. So that guy is still present in the overall reaction, which means it cannot be an intermediate. So again, an intermediate can only be the one where it gets completely canceled out. It is not found in the overall reaction. So in this particular case, even though we reduced down the NO2, it is still present in the overall reaction, which means it's not an intermediate. The NO3 is the only one. Now, how do we know, what can we say about the rates of step 1 and step 2? So this is where these elementary steps come into play, and basically it will help us determine, is this a good or plausible sort of rate law? So again, the one thing that we do know is experimentally, like you did yesterday, they were able to determine that the rate law for this experiment is what was given there. Now, for each of these individual steps, which are elementary steps, we can write a rate law. So for example, the rate law for our first step would be K, and this is basically 2 NO2s, which means that it'd be the concentration of NO2 squared. Again, this is the one place where we can use the coefficient as its orders. If we wrote the rate law here for the second step, the rate is equal to K times our NO3 and our CO. And that would be the rate law for the second step. So the one thing that we know is if this is a good mechanism, which it is believed to be, the rate law for the rate determining step or the slow step in the mechanism should match exactly the rate law that was found experimentally. And if we look at this, we could hopefully see that it is actually the first step which has a rate law that matches the one that was found experimentally. What that would tell us in this case is actually the first step in this mechanism is the slow step. It is the rate determining step. So what really determines the overall rate of this particular reaction is that slow step. And in this particular mechanism, it would be the first step. Once that first step happens, the second step will probably happen relatively fast. But overall, it is the one that's going to determine the overall sort of rate law for this reaction. So step 1 should be definitely slower. And obviously step 2 should be much faster than step 1 in this case. So this is one type of mechanism problem where you basically can look at a mechanism. If you know the experimentally determined rate law, you can use it to figure out which one is the rate determining step. Now, there are other types of mechanism problems, which we won't go into, but there are other types of mechanism problems where it's kind of like a proof type problem where they give you a mechanism with several steps and they want you to prove, is it a good or bad mechanism? So you have to do some math to sort of do that. But ultimately, you're looking for those two things still. Does all the steps add up to the overall reaction? And does the rate determining step, the slow step in that mechanism, match the rate law that was found experimentally? By the way, this is the other way that in a mechanism type problem that you can figure out the rate determining step. They are typically sometimes labeled fast, slow, fast, and the one that is labeled slow would be your rate determining step or your slow step. And in this particular one, this should have for step number 2 a rate law that matches the one that's found experimentally. If you find after you do the math that the second step does not match the experimentally found rate law, then it is a bad mechanism, which can happen. You could have a bad mechanism or a good mechanism. And again, those are the two things. Questions on that there? All right, that is kinetics. There it is.